That way everything is official. Not going to forget that again. So, welcome back. Happy last week of classes to everybody. No matter how stressed you are all feeling right now, I can tell you it is finite. It will come to an end. Perhaps not soon enough, but we will get there. So this morning I updated grades, so we should be caught up with respect to everything that has currently been done with all, let's see, in this class we have 4 homeworks and 7 formative assessments. Your last homework is not due until the end of finals week. Just as a reminder, next week during finals week, we are not meeting as a class. However, I am going to be sitting on Zoom during all of the times that I would normally be teaching or hold office hours. So that'll be Monday at 3:30, Tuesday 12:30 to 3:30, Wednesday at 3:30, Thursday 12:30 to 3:30, and I'm taking Friday off. Emails are of course welcome at any time if you get stuck on any part of example 7B. Or sorry, the homework that goes with 7B is what I meant to say, homework 5. What did I tell you guys about my deal for course evaluations a week ago? Well, how many did I say you had to have? Because it didn't get recorded. Did I say 19 or 20? Do you remember? Nobody remembers? Okay, so there's 21 of you completing course evaluations. Right now you are up to 12. So my deal is, I'll be generous, let's say 19. If 19 out of 21 of you do a university course evaluation, everybody gets a point of extra credit. Each of you can also complete a separate Qualtrics survey that you should have been emailed last week, and if you complete the survey, you will get yourself a second point of extra credit. If anybody needs me to resend the link to that, please let me know, and I'm happy to do so. Otherwise, I will send out a reminder about course evaluations probably tomorrow, because the universities close on Saturday. The Qualtrics survey doesn't close until the end of finals week, though, so you've got some more time on that one. Otherwise, that's about it. In this example, I sent out an email, I think when I put the homework up, but just to make sure that everyone's aware, I found an extra estimation option in Elmer, in R, that I'm not entirely sure what it does, to be honest, but it's the algorithm that much more closely matches what SAS is doing under the hood. So the numbers were matched a lot closer after I switched to that. So I updated example 7B to include that extra snippet of code. So when you start your homework, please go get the newest version of the R files if you're going to use R, and that will allow you to complete it without the frustration of being off in the second decimal place. I checked everything, and I can verify that it should work. All right, so any questions on any of that stuff? Due dates, homework, stuff like that? No? Good. So then what my plan was for today was, because your last homework is covering the polynomial models that are the second half of this example, I wanted to make sure that we did that first. And then with whatever time is left today and on Thursday, we can talk about the story problems in the formative assessment. And if it looks like we'll have extra time on Thursday, then I will make up some more story problems for us to go over as well. Because eventually what I'd like for each of you to be able to do is to be able to put yourself in the perspective of an analyst and figure out what the model would need to look like in order to answer a particular research question given a particular longitudinal design. Using the skills that you've at least from this class. There's a lot more to longitudinal analysis than what we can cover in one semester, though, of course. All right, so then shall we jump back into this? Would that be useful? While you're chewing, at least. It's like lunch and learn, right? Like one of those seminar thingies here. All right, so this story behind these data, just to remind you what we're talking about here, these are 6 occasions of practice in a speeded response time task over a 2-week period. So we're looking purely at the extent to which our participants who are older adults improve in their response time as a function of practice. We're predicting individual differences in the extent of their improvement from time invariant predictors. Baseline age, which I've centered at 80, which was near the middle of that distribution. Abstract reasoning, which is a measure of fluid intelligence that I centered near the mean of the variable at 22. And then also education, which was a continuous predictor that I cut up into groups of low, medium, and high, just for the sake of showing you what it would look like to have a grouping variable, not because it was a good idea. So last week, we went through piecewise models with these data, where the basic model looked like this. This is page 2. We had a linear slope for practice between sessions 1 and 2, a second linear slope for practice between sessions 2 and 6. And so in that respect, the two slopes are not hierarchical. They work together to describe the trajectory in a discontinuous way, but you don't necessarily need to think about one versus the other in a way that polynomial slopes are hierarchical. So that's the extra layer of complexity when you have quadratic terms, is trying to remember and understand what the linear terms mean when they're conditional on the quadratic terms. So we went through a bunch of models. We ended with three-way interaction terms, which are not so scary when you actually work through them. But I don't think I have any three-way interaction terms other than time by something in the examples that we have for the polynomials, because I'm only so mean. All right, here we are. This is where I wanted to pick up then. So stuff we haven't talked about yet. Model 2A, this is on page 18 of example 7b. So going through the same process, but now describing what it would look like to have a quadratic model as the basis of change rather than a piecewise model. So model 2A, I'm calling unconditional, and just as a reminder, what do I mean by that? What does the term like unconditional model for change signify?
And there's no added covariates?
Yes, just time. So the idea is that we would first figure out what all is needed in the model with respect to time, both in the model for the means, so the fixed effects here that would predict average change, gamma 0, 0, 1, 0, and 2, 0, the random effects that allow individual differences in each aspect of change, as well as any heterogeneity of variance across time in the R matrix, or any additional residual correlation in the R matrix. So all of that stuff would need to be sorted out prior to including the predictors that you care about in most cases. And just to remind you, the rule is when you're talking about how to form an instantaneous linear slope for any occasion, we have to multiply the quadratic coefficient by 2. So what you get out of this model for the quadratic slope is half the rate of acceleration or deceleration of the function. That's why we have to multiply it by 2 to get to the full rate. So twice the quadratic is how the linear rate of change changes per unit time. I'll say that again. Twice the quadratic is how the linear rate of change changes per unit time. It speeds up or it slows down. So the combined equation just using the fixed effects to predict response time is right here, where we would fill in the fixed intercept, multiply the fixed linear slope by whatever the coded value is of time for that session, and then multiply the quadratic slope by time squared. So when you're building your statements to get predicted outcomes or predicted linear slopes, if you're computing a predicted outcome, everything goes in the equation. Intercept, all the slopes, all the stuff, and the multiplier of the quadratic term is time squared if you're creating a predicted outcome. If you're creating a predicted linear slope, then the only thing that goes into that function are fixed effects that have to do with time. So it starts off with just whatever the fixed slope of time would be at time 0, and then we put in as the multiplier for the quadratic however time is coded at that occasion you want the linear slope for, and then multiply it by 2. So 2 times time if you're building a linear slope, time squared if you're building a predicted outcome in terms of what multiplies the quadratic. Okay, so a little bit of review there, but that's a tricky concept, so I want to make sure that that's clear. Questions or comments on that much thus far? All right, Zoomers, you can hear me, see me okay? I'm assuming as much, but that's always good to check. There are some thumbs. Excellent. You get a thumb back. So then in terms of code, all the stuff you've seen before, new pieces relative to what we had in previous examples is asking for predicted outcomes so that I can square them with the original outcome square the correlation, excuse me. So OutPM here builds a new data set that has a column of predicted outcomes that I'm then asking it to correlate that new column called pred with the real outcome. That's how you would make a total R-square. The same thing happens with the predict function in Stata. That generates a new column in the data set that is predicted values from the fixed effects, which you can then correlate with the real ones. And the same thing happens in R with reform.na, which means don't put the random effects in, only put the fixed effects in. So one thing that is going to make our results potentially trickier in this context is the relationship between the linear and quadratic time slopes. So only when you have mean-centered time do you have a chance at having your linear and quadratic random slopes be uncorrelated. Otherwise, they're going to be correlated in part because of the way that we've centered it. So right here, the first piece of output that I have is the G correlation matrix. So this is the model implied correlation among the random intercept and random linear, which has a negative relationship, random intercept and random quadratic, which has a positive relationship, and this one right here between linear and quadratic. So they're nearly perfectly correlated. And that's part of the reason I think why differences in the algorithms used to estimate these models between, say, SAS and Stata and R might come up with different solutions, is how it tries to deal with the fact that these things are very nearly the same. So this is something to watch out for in practice. If it starts to go to 1 and it kind of stays there, that might mean you either need to change your centering or potentially reduce the complexity of your model. You'll start to get non-positive definite messages, which refers to either one of your variance components going to 0 or the correlation between them potentially wanting to go out of bounds. So that's more likely in these kinds of models where you have time and time squared because they're going to be related. Otherwise, we got all 7 parameters in the model for the variance here as part of my list. I got my fixed effects. So 1945 then is the predicted outcome, which is response time, when time is 0. So I have to know when that is in order to interpret it. Looks like it's going to be at session 1 based on my coding scheme. Minus 120 is my linear rate of change on average. Can I stop my sentence there or should I keep going? Got to keep going, right? Because it's which linear rate of change, right? The whole point is that this is a nonlinear function where the rate of change changes. So which occasion is this slope for specifically? Session 1, and how do I know that? Because that's where I set the intercept. It's up to you. So it's not always going to be the first occasion. It's however you coded your model. In this case, it is, but just as valid would be to put session 6, for instance, the end to be your intercept. Then you'd predict individual differences in where people ended up as opposed to where they started. Is one of those more right than the other? Nope. Would the model fit differently if I centered at session 6 instead? No. Would it generate different predicted values? Not predicted outcomes? It would not. But if I centered at session 6 instead, which of these three numbers would change?
The intercept?
The intercept would for sure. Yep, this would be the slope at 6. How about this one? The quadratic slope. If I change my centering of time, would this number change? It would not, because there's nothing else in my model that makes this two-way interaction conditional. It's the highest order term. That means it's unconditional. Another way to say it is that the way that the linear slope changes is constant. It changes by a constant increment every session. So 1 second here. Got a runny nose from being out in the cold. All right. Or it could be a runny nose from my kid being sick for the 18th time this semester. Who knows? But that's why we wear masks, so that I don't pass on my runny nose to any of you. So there's several questions in your homework asking about, like, what is this conditional on? Is this the linear slope on average? Is it at time 1? Is it at this, for this person, for that kind of person? What I'm asking in terms of who it's for is, like, is this conditional on any other higher order term? If so, then you have to know where that higher order term is at 0. If not, then it's constant. So in this model, the intercept is at session 1 because of these two predictors. The linear slope conveyed by this fixed effect of time 1 is specifically at the first occasion because that's when this one would 0 out. So it's conditional, but this last quadratic term is not conditional. And then if I were to put this number in a sentence, how do I talk about it? What is this quadratic coefficient doing to the linear slope? You got 4 choices.
Less negative.
This is a less negative. So for every additional occasion, my negative linear slope becomes less negative by how much? And don't say 13.
27.
Yeah, 27-ish. 2 times the 13 is the answer. So the rate of change then is slowing down, is the way that I would think about that. That's what less negative would mean. It's getting closer to 0. And eventually, if we follow the curve, it's going to be predicted to come back up again. On the whole, the outcomes for response time that are predicted from these two fixed effects are correlated with the actual response times, 0.19. If I take that correlation and square it, I get to my total R square. So in your homework, there's questions like, how much of the total variation in well-being is predicted by the model? This is what I'm asking for, is total R square. All right, I think that's all I wanted to say about that. Questions thus far? Sir?
Should we report total R square and pseudo R square together, or do we have to choose between one?
So in this context, I'm reporting total R square as a baseline for how much of the model is just change on average, then how much more variance did I explain by adding this and this and this predictor. In this application, pseudo R square would not be relevant because we've already built the model, but pseudo R square would have been relevant in adding each of these fixed slopes. So I would have said how much of the residual variance did time and time squared explain. So I would have already done that part.
Oh, okay.
Yeah. Question from the Zoomers, could we go over the linear contrasts in R? It may come up later. Which linear contrasts? The contest
Well,
one.
if there's like a categorical variable and you're trying to find the difference in, you know, the time, in, you know, the effective time or whatever.
Oh, okay, yes. We will go over that in about like 3 models from now for a categorical predictor, but we'll go over it for each predictor for continuous ones.
Okay.
Is that good?
Thank you.
Okay. Yes, and I did, by the way, I looked back at the code that I thought I had made an error in. So thank you for reminding me of that, Nathan. The model that had education in it for the piecewise models, I looked at my code standing here and I thought, that doesn't look right. And then I went back through what it actually was doing and it is right. So the code that as I had presented it in class is correct. So this was from the model that had education as a grouping variable. By the way, this is the new chunk of code that controls which optimizer is being used and makes the results closer to what SAS does. In these contest 1D statements, so I had, for instance, low versus high on the intercept, and then I looked at this and I thought, this doesn't look right because there's not a positive one to match. That's because this contrast was already given directly by the model, but the way the model had phrased it was high versus low. So to get low versus high instead, I take whatever the coefficient was and I multiply it by -1. So these first two rows are correct because they were already model implied differences given by the fixed effects directly, just in the wrong direction with 3 as the reference group. And then this is the one that's a linear combination of the two. And so that one then is the difference of the two slopes that differentiate low versus medium from high. So this was correct. I just looked at it and thought, that doesn't look right, but it is, because R is set up differently than the other packages. So thank you for reminding me of that. That didn't answer your question, but it reminded me of something I wanted to say. But yes, we will go over the statements for asking for simple slopes and differences and things like that. All right, let me find where I was. Here's where I was. Okay. Model 2B on page 19. So just as we did with the piecewise models, the first thing I'm going to add here is chronological age, which is a time invariant level 2 macro between person predictor, because people are not aging during the 2 weeks of this study. So I'm asking the question, do people who are older have different degrees of practice? Do they start out differently? Do they improve at different rates? So because I have 3 level 2 equations here, people differ from each other in 3 different ways. U0 is how they differ from each other in their intercept, which in this model is specifically at predicted session 1. U1 is how people differ from each other in their linear slopes. And because there's also this random quadratic U2, the U1 random linear slope is also conditional at session 1. It's individual differences in the slopes at that point. The U2 means that the extent to which people differ from each other is going to change as time goes on, because the quadratic slope then allows differences in acceleration or deceleration. So because I've got 3 different ways people differ from each other, age has 3 different roles that it can play. So then in terms of how we would build predicted slopes as a function of different covariates, in this model, here is my combined equation, where I've substituted time with capital T to save myself some typing. So age is predicting the intercept, age is predicting the linear slope, age is predicting the quadratic slope. So that means then if I want to compute a linear slope for any level of its moderators, I start with the fixed linear slope, which would be specific to time 0, as well as specific to age 0. To get to a linear slope at a different occasion, I have to multiply the quadratic slope times time by 2, so twice the quadratic. And then to get to what the linear time slope would be for somebody who's a different age, I would multiply the cross-level interaction of age by time by whatever age I want the slope for. And one more piece. There's also age by time, which technically is a 3-way interaction. So in this case, I would also have to fill in as my multiplier age and then 2 times the value of time that I would want it for. So that's going to be the tricky one. Quadratic time is a little more straightforward. This would be the quadratic slope for somebody who's 80, and then I would plug in whatever age I want the quadratic slope for as my multiplier. And for age, gamma O1 is the main effective age, which would be at time 0. To figure out what the effective age would be at any other time, I would plug in time or time squared in these terms right here. So that is the logic by which the programming statements below were created. So in SAS then, here's my 3 new fixed effects. I'm asking for a Wald test that lumps the 3 of them together. So asking for a joint hypothesis test for all the age slopes. Here are predicted linear slopes at different occasions for different ages to show how the math would work out. So at session 3, then that would be time is coded 2 multiplied by 2. Session 5, time is coded at 4 multiplied by 2. If I want it for a 74-year-old, then I would plug in -6 for my age 80 moderator. And if I want to have session 1 and age 74, then it would be 0 times -6 builds that term right there. Otherwise, it's for instance, if this is coded 4 and this one was coded -6, then this is -24. So once you've built sort of the ingredients, then you can figure out what the multiplier would be a little bit more easily. Quadratic is a little more straightforward because then all you have to do is multiply by the age at which you want the quadratic slope. Same with the age slopes, a little more straightforward because you just fill in time and time squared. All right, Stata code looks pretty much the same. In R, we have this row of fixed effects. So I've helped several people with this, by the way. Don't forget the little I right here. Can anybody tell me what I stands for?
Insulator.
Insulator. What the hell is that?
It contains it. I don't know. It's like a thermos, I guess.
Insulator sounds like the stuff that's up in my attic, like insulation. I don't know. Well, okay, so don't forget your insulator. Otherwise, you're not going to have time squared appropriately. And if you can't ever get it to work, making a new squared variable, also an alternative. So this is the main effect, so to speak, of time squared, the main effect of age, the interaction of age by time, and then the age by time squared interaction would look like this.
Actually, I take it back. It's inhibit.
Inhibit? Oh, that makes
Yeah.
even less sense.
Yeah, I know.
I give up. I give up. I'm not going to try to understand. I'm just going to accept that this works. All right. So then, was this the kind of thing that you wanted to go over, Zoomers, in terms of the linear contrasts? Or was it with specific for categorical variables?
Mine was specific to categorical, but I think this might help
Okay.
either way.
So first of all, how do I know how many of these numbers I need?
Fixed effects.
Number of fixed effects. How do I know what order I put them in?
Looking at the output.
Looking at the output. So what I usually do is write it out, then see what order it turns out if they rearrange it, and then change my writing to match what it's going to be. That way everything's internally consistent. But yes, it's the order in which it shows up in your output. So for instance, the first 3 lines here are asking for predicted linear slopes for people of different ages at different occasions. So the one that we get out of the model is the linear slope at session 1 specifically, and for an 80-year-old specifically. That's why this line right here is sort of the reference point. Because all it contains, here, let me make this a little bit bigger. Try to. There we go. This one. Okay. All it contains is a 1 where the fixed linear slope is. Because that's the only situation in which that's the only term that would apply. Everything else that has linear slope in it zeroes out because we're at the centering points. So these first 3 here, these are all for a 74-year-old. So that's why the term of age by time has a -6 in it, because you're filling in for age, because time is a thing we're trying to estimate. The second column, all the way through all of these numbers, has a 1 in it, because what we're trying to estimate is the linear slope. Why does the first column have a 0 all the way through?
That's the intercept.
That's for the intercept. And why don't I need the intercept in my prediction?
You want the slope.
Because I want a slope. Exactly. The intercept does not apply in my prediction. Exactly. So that's why these are zeroed out. If I had asked for a predicted outcome, then I need the intercept, and I need everything that's in the equation. Okay, so let's do, say, this one right here. So this is at session 3. So I need 1 linear slope. I need to tell it for which occasion I want the linear slope. So that the answer to that is 2 times the occasion, goes in the quadratic spot here. Next comes a column of zeros. And why are these all zeroed out across all these lines? What term does that fourth column of zeros refer to?
Age.
The age main effect. Now, why does it stay turned off the whole time here? If I zero something out, I think of that as like a light switch that's been flipped off, like it doesn't get to contribute. Why is my question.
Because that slope is conditional on that slope equals 0. H calculating time is conditional now. because
So
of the
which
interaction.
fixed effect does this zero column refer to?
The main effect of H,
Main effect of age. What am I trying to estimate here?
the linear.
The time slope. Yeah, see, this is where, like just saying slope is like not nearly specific enough. We got to have very specific words here. I am trying to estimate the linear time slope. Does this term have linear time slope in
No.
it? Does not, so it doesn't apply. So only the fixed effects that have the term you're trying to estimate could possibly have values. That's why the intercept drops. That's why the main effect of age drops. Everything else has time in it somewhere. So recapping, first column is zeroed out because it's for the intercept. Intercept does not contribute to a time slope. Second column is all ones because at a minimum, to compute a time slope, we need the fixed time slope as a starting point. The third column is time times 2. That's going to multiply the quadratic. The fourth column is zeroed out because it refers to the main effect of age that does not have time as part of it, so it's not relevant. The next column, number 5, this is for age by time. So all we have to fill in is what age we want the time slope for. So it's -6 because this is for a 70-year-old, 74-year-old, zeros for the 80-year-old, and +6 for the 86-year-old. And then the last one, all you have to do is the math that you've already created. So this is age by time by time. So we've got time by time and age. So those column 3 and column 5 multiplied together give you the ingredients for the last column. So 4 times -6 is -24. Just don't forget your minus signs. That's an easy thing to mess up. So this is the hardest kind, I think. The linear time slopes are difficult. Did I ask for any of these in your homework? I didn't? See how nice I
For
am?
that multiplication, not.
No, not for this one. But,
Yeah.
but in case you want to do this in your life, I wanted you to have a little bit of an example to follow. Now, I'm going to be honest with you. This is one where I didn't trust myself, and I decided to check my own math. How did I do that? How could I verify, for instance, that this one is correct?
Changing the parameters,
How do I
Yes, sir.
change them how?
centering points at that value.
So if I wanted to get for sure that the linear time slope is correct for session 5 and age 74, I recode time so that session 5 is the 0. I recode age so that 74 is the 0. Then the linear time slope that shows up on my output should be the result of this calculation. So this is how you can check your math, is figure out what it would be if you recentered the model. That is originally how I learned how to do this. Recenter the model, re-estimate. Recenter the model, re-estimate. Okay. Quadratic time slopes then are easier. So if what I want to know is quadratic time, then there's only 2 terms that could possibly apply. Time by time and time by time by age. Nothing else has time by time as one of its ingredients. So the column of ones here in the third spot is for time by time, and then I fill in the age at which I want the time by time slope. Okay, how are we doing? Yeah? Once you see it, you can't unsee it. It's like one of those magic eye posters. Or those optical illusions where you can like see like, you know, the figure in the vase or whatever, one of those things. Once you see it though, you can't unsee it. It just takes a really long time to get to that point. All right, age slope at different occasions. This one is much more straightforward. Why are the first 3 rows all zeroed out in these lines right here?
Because those are for time.
Because they have to do with the intercept and with time. And what I want is the age slope. So everything that would be relevant has to have age part of it. So the 4th column is a 1 because that is for the main effective age, which is what I need at a minimum. The column after that is whatever the time is coded for that session, and the last column is time squared for that session. So that one's a little more straightforward. And which of these would I get on my output if I did nothing? Which of these is already somewhere in my output? Don't overthink it. This is softball.
The best one.
The first one, yep, the one that has just, that's not a linear combination. That's already on my output. Why did I put it here? So you could see the pattern. In practice, when I have a bunch of these things to do, I do tend to write out the ones that I have already just so that they're nicely labeled and part of the same table. That way I don't have to like think about it too much when I come back to it later on. Then age by linear time, conditional on each occasion. So because we have age by time in the model, the age by time two-way interaction is conditional. So the first one tells you that what you get out of the model is the age by time interaction conditional at the first occasion. Age by time means that what it would be differs at subsequent occasions. So how age affects the linear time slope changes throughout the study. Yes?
Now, the mean effect of the quadratic time slope is conditional on at baseline 2?
The main effect of the quadratic time slope
slope
is not conditional on time, but it is conditional on age.
Oh, okay.
So that one was like these 3 right here. So time by age means that time by time is conditional on age. And age by time is conditional on time. But time by time is not conditional on time. What would I have to do to make time by time conditional on time?
Cubic effect?
Cubic. Yeah, then it would be. Yeah, that's too much, even for me.
Lisa?
Yeah.
So in this case, the main effect of the quadratic time slope will be across the study, even with this interaction.
Yes.
Great.
The quadratic is unconditional with respect to time, but it is conditional with respect to any moderator that it interacts with, including age.
Great. Thank you.
Yep. All right, so in practice, you wouldn't need to necessarily write out all these things. And don't write them all out for your homework either, okay? Is everyone listening? Don't do this. Just get the model and then just see which questions want things. So I'm only asking for maybe 1 or 2 extra calculations, not all of them. I'm not that kind of mean. All right, shall we look at the numbers? Why not? Okay, so I didn't write out the interpretations this time, but I did tell you which fixed effects is which. So solution for fixed effects here. I've got a dividing line here as to what we had before and what we've added. So intercept, linear slope, and quadratic slope, because age interacts with each of them, this is essentially a reference growth curve for an 80-year-old. Not just a reference point, but a reference curve. So someone who is 80 is predicted to start out at 1950 milliseconds. Their initial rate of change is an improvement of 122-ish milliseconds a session, but that initial rate of improvement slows down, I would say, is less negative by 28-ish per session. All right, slope of age. It's significant. How do I talk about it?
Difference in the intercept per unit, difference in age.
Yep, difference in the intercept specifically per year of age. So for every year older you are when you start the study, you're predicted to have a higher response time by 29 milliseconds. And this is conditional at what occasion?
1.
Yeah, the first occasion, because of these interaction terms. Let's do time and time by age. What happens to my linear time slope in older people?
Becomes more negative.
Yeah, this is a more negative, minus 121 and minus 5. So the way I would talk about it is for every year older you are, your initial rate of change at session 1 is more negative by 5 milliseconds. So 5 milliseconds a year, however, not really significant. That's okay though. Now how about this one? What does age do to my quadratic? Zoomers, you can play along too. I'm watching the chat. What does age do to my quadratic?
Makes it more positive.
More positive. Now, what does that mean if we think about the fact that it's a positive quadratic paired with a negative linear?
The rate of deceleration increases.
Yeah, the rate of deceleration increases. So, or in non-physics terms, they slow down more. So if you think of it as kind of a leveling off of the slope, like it's a stronger leveling off if in older people, just not significantly, but that's the direction it's going. So at this point, a picture would probably help quite a bit because it's difficult to describe these things this way. Okay, how are we doing? Not so bad. If we go the other way, this is what makes quadratic models tricky. So this is the age slope at the first occasion, right? What happens to it initially as time passes? Which of my 4 is this?
Less positive.
This is a less positive. But then this thing kicks in. So the age slope looks like it's getting smaller over time, but the extent to which that happens is reduced. As time goes on. That's as good as I can do on that. That's a hard one. But the point of the story is that time by age right here, that's conditional. It's conditional on the quadratic interaction term. It's easier to understand this pattern of how the age slope changes over time, I think, if you look at the age slopes per occasion that I computed earlier. So the age slope is predicted to be 29. So for every year older you are at the first occasion, you are slower by 29 milliseconds. If we just look at the change in this age slope, 29 to 24 to 20, so the age slope is being reduced as time goes on, but the extent of that reduction slows down. So the slowing down of how the age slope changes over time is because of the time by age term. So age matters less as time goes on, but then that effect starts to kind of die off. So a bunch of different ways you can think about that. All right. So joint hypothesis test for all 3 of my age slopes says yes, it's a significant contribution. The size of the contribution in terms of total R square, so my new predicted outcome is correlated with my real 1.32. If I square that, that gives me my total R square. Relative to the model that just had time and time squared in it, that's an improvement of about 7%. So age is responsible for about 7% of the overall response time variance. If we go to pseudo R square, which is another thing I did ask in your homework, I do remember that one. the formula for pseudo R-square, what it was before, minus what it is now, divided by what it was. So if we look just at UN11, what does that refer to? What was the first random effect that I had listed in my code?
Random intercept.
Intercept, and that's true in all the packages. So then the intercept variance specifically was reduced by 10%. Which term did it?
The main effects.
The main
of
effect
the
of?
predictors. H.
Of age, yes. So there are terms in your homework that say specific effect size. This is what I'm talking about. Each new fixed effect that you've added for a time invariant predictor has a job to do. The main effect of age explained 10% of the intercept variance. Something explained 3% of, what's the second term that's random? What comes after intercept?
Time.
Time.
Linear.
So linear time specifically. So we got about 3% of the linear time slope variance was explained by which fixed effect? We already did main effect of age, so there's only two other possibilities. Is it age by time that explained the time slope variance, or is age by time by time?
Is by
By
time.
time.
Age by time. So then what did this one, which is time by time?
Is by time.
Age by time by time, yes. Yeah, they all match. And how about level 1 residual?
Nothing.
Should not have been explained. So this is as it should be because we didn't add any level 1 predictors. We didn't add any cross-level interactions with level 1 predictors that don't have a random part. So,
Lisa?
yeah.
You said main effects for those random components. Those are cross-level interaction or they are main effects? How
The,
should we call them?
the main effect of age, just age by itself, is a level 2 fixed effect. Age by time is a cross-level interaction. Age by time is also a cross-level interaction. Yep.
Thank you.
Yep. Yay. There we go. Not so bad. So as I had done in the piecewise models, I'm keeping all three effects of age, even though only the main effect was significant, so that I can say I've controlled the entire growth curve for whatever effect of age there is. I then add reasoning. So to what extent does fluid intelligence predict improvement in this task after controlling for age? That's my question. The predicted instantaneous linear slopes get even uglier, as you might imagine. We add reasoning as another thing that the quadratic time slope is conditional on, and the effects of age and reasoning are not conditional on each other. So 3 new terms, asked for a joint hypothesis test. Here's a demonstration of how I would ask for predicted linear slopes, holding age at 0 and then doing particular levels of reasoning. So same logic as before. Quadratic slopes conditional on reasoning, reasoning slopes conditional on time, and reasoning by linear time interactions conditional on time as well. Fun stuff. All right. Yeah, so nothing else that's relatively new in the code for those things. I wanted to show this model in particular because there's something interesting that happens with it. So now in R, we're up to that many zeros in each of these statements because we have a lot of fixed effects. So same idea as before. Linear terms first, multipliers that have to do with time or time squared for the moderation effects. Quadratic terms, multipliers that have to do with time by the moderator, and so on. Okay. So if we go down to my fixed effects, here's what happens. So these 3 terms right here, what are they conditional on? Intercept, linear time, and fixed quadratic time. Are they conditional on age?
Yes.
Yes. Are they conditional on reasoning?
Yes.
Yes. So I would say that these 2, intercept and linear time, are specific to time 0 and they're for an 80-year-old, and they're for a 22 reasoning person. All three. Time by time, not conditional on time, but it is conditional on age because of this one. It is conditional on reasoning because of that one. How about the age slopes? Are they conditional on reasoning?
No.
They are
No,
not.
yes.
How about the reasoning slopes? Are they conditional on age?
No.
They are not. So in terms of the pattern of effects, what happens to people who did better on the reasoning test, according to this fixed effect?
They would perform better.
Yeah. So a negative slope in this context means they're faster. Faster when?
Basement.
Baseline, because of these. If we only had just this slope right here, it would be at all the occasions. It would be a constant shift, like a parallel line situation. So people who did better on the reasoning test, for every additional correct answer, their response time at the beginning is predicted to be significantly lower by 27 milliseconds session. Let's see, let's do that one. What happens to smarter people's slopes initially?
More negative.
More negative. Stronger or weaker?
Stronger.
Stronger, yeah. More negative or more positive, those are stronger effects as a function of the moderator. What about quadratic slopes? Smarter people have what kind of quadratics?
More positive.
More positive, so more of a deceleration, more leveling off, that kind of thing. However, these two interaction terms, cross-level interaction terms as I would call them, because time is purely level 1 and reasoning is purely level 2, they're both non-significant. So assuming that reasoning doesn't have any special status that I need to control for or someone's going to yell at me, do you think that I should dump them both or dump them one at a time?
I would say both.
You think both?
Yeah. If you remove one of them, what happened with the other?
Oh, let's find out. Yeah. If I had to pick one only, if I don't want to do both, if that made me uncomfortable, which one would go first?
Sine quadratic.
Yeah, the highest one, right? Because this term right here is conditional on the quadratic. So I'm going to dump this one and show you what happens. However, I'm going to have a split screen here so we can see the previous results against the new ones here. Okay, scroll, 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 scroll. Scroll, scroll, scroll. Oh, gotta scroll way longer than that. That's what happens when you have a 36-page handout. Okay. Almost there. Almost. Okay, now we're back at that model. Oh, add a picture too. So this is what the curves would look like from that model. The top line is somebody who has the lowest level of reasoning, so they're the slowest. The bottom line is somebody who has the highest level of reasoning, so they decelerate more. They have a more leveling off. All right, so what happens then if I take out the reasoning effect? So do you see the hole in the equation right there? This is my convention, by the way. I don't know that most people would do this, but I tend to do this on purpose. I deliberately spaced the U over so that it tries to stay aligned to show the hole. Because then it looks like a grid and you can see what's there and what's not there a little more easily. For the same reason, like the next term that I add to the model, I won't call it like 2, 2 because that spot has already been taken. I would go like 2, 3 for the next one, skipping over the number. That way it's like internally consistent in terms of the equations across the versions of the models. But this is the hole I've created here. Okay, lots of code, lots of code, lots of code, lots of code. Okay, here's what happened. So with respect to reasoning, there. So my main effect used to be minus 27, now it's minus 32, but I have about the same inference. Time by reasoning used to be minus 3.6, now time by reasoning is actually positive and significant. So this is for two different reasons. Number one, what did you learn about collinearity back in regression land? Yeah, do you think that time by reasoning and time by reasoning are going to have anything in common? Yeah, quite a bit. Particularly because we centered at the beginning of time, as opposed to mean centering, which would make them as uncorrelated as possible. So yeah, the general things that you learned about predictors that are correlated still apply. It becomes more challenging to differentiate their unique effects when two correlated predictors are in the same model than when each is separate. So if we look at like the standard error for that time by reasoning effect, it was 4.5-ish. Now it's down to 1.2. So it's much smaller, in part because it doesn't have the competition of time by reasoning, but also in part because it means something different. In the previous model, time by reasoning was conditional at time 0. In this model down here, it's not. So the coefficient and the standard error means something different. In the bottom model, what it's saying is that the way that reasoning affects the slope is constant throughout the study. People who do better on the reasoning test have less negative slopes, the end. So this term is no longer conditional on time. How reasoning affects change is constant throughout the study. So I mean this to be a cautionary tale. When you're working with polynomial type models, linear and quadratic terms are going to be highly related. I would remove the quadratic terms and then re-examine the linear to make sure that you're not accidentally removing things that should stay. There. Okay. Does that make sense? Maybe? Still with me? Hanging in there? I know it's 1:33. I'm pushing my luck. Does it count that we started like 10 minutes late? Do I get those like 10 minutes back in terms of cognitive energy? Like a coupon. Like I'd like to redeem the 10 minutes I wasted at the beginning of class getting my screen to work. They're like, no, it doesn't work like that. All right, so yeah, here's my new picture. So after taking out the time by reasoning, then the picture looks a little bit different. The extent to which we have different slopes as a function of reasoning is constant throughout the study. But yeah, that effect is significant, but not that strong, it looks like. All right, and yeah, so relative to the age-only model, reasoning explained 10% of the variance. It added to the linear slope variance, and it explained none of the quadratic. So these things in particular are going to get wiggly because they're so highly related. All right, last model, I promise. So here is what I meant by leaving the hole in the equation. I'm adding in education group, which is a 3-group predictor. So that means how many contrasts do I need to represent education group? 2. So the effect of education on the intercept is gamma O3 and gamma O4. The effect of education on linear time is 1,3 and 1,4. And the effect of education on quadratic time, I have labeled as 2,3 and 2,4 to keep it consistent. There is no 2,2 term. So this is my standard. This is the way that I do things because I'm trying to make the point that reasoning could have been here I tested it, I took it out, so it's kind of like I'm just reserving that fixed effect symbol for what that parameter would have been. So the way that I have worded these contrasts in the equation is meant to help us keep track of who the reference is in terms of the model fixed effects. The high group is actually the reference. So one contrast is going to tell me how the low group differs from the high. The second contrast is going to tell me how medium differs from high. The missing one, then low versus medium, I have to ask for as a difference of those two slopes. So then in terms of our conditionality, linear time is all of this stuff. Quadratic time is just age and education. And age and reasoning are not conditional in education, given the lack of interactions. So education group is the predictor. To denote it as categorical and have the program make the dummy-coded contrasts that it implies is class and SAS. So education group, those are the 6 terms right there. In Stata, it's IDOT with the added IB last because I'm moving the reference category to the last group rather than the first, which is default. And in R, I have it as factor. So the first one, let me find it again. Right here, right there. So this is a good example of where I had to rearrange them. Rearrange, I've dropped a syllable del. Rearrange, does that work? So in all my other packages, like I wrote them in order in which I added them, right? So these came first, then I had age, then I had reasoning, then I had education, right? I had to reorder them in R to match the output. So R was like, nope, you can have time, then you have to have all your main effects, then you can have your interactions with time. So initially, this was in a different spot than I thought, and none of my answers were working, but that was why. I wrote it to be last, third to last, and I had to move it. The contest MDs lump together effects of education, and the contrasts for the group differences then are right here. So low versus high is what I wanted. That's already in my model, but it was backwards. So I listed it as a -1. Same with medium versus high. Low versus medium is the one that's implied. And so this is just asking what's the difference between education groups and the intercept, what's the difference in the linear slopes, and then what's the difference in the quadratic slopes. So it's the same pattern, just in a different spot, depending on which type of education effect we're looking at. Okay. Questions on any of those codes? All right, I do not believe, well, you have a 2-group example in your homework, but not a 3-group. 2-group is easier. So that one you can just represent as a dummy code. You don't have to have a factor variable. Same story as with the piecewise models. It looks like there's no differences as a function of education on the intercept, no differences as a function of the linear slope, no differences as a function of the quadratic slope. Wald test lumping the contrasts together, non-significant for the intercept, non-significant for linear, non-significant for quadratic, non-significant overall. Education does not predict response time at the end. But here are the pairwise differences. That way you can look for each combination as to whether there are any differences across the levels of your predictor. And conditional means. And differences of means. And R squares, and that's it. Then we get into words, which means we're done. And it's 1:40, which is a good time. All right, how are we doing? Yeah, we did. That's it. Any questions before I shut this thing down? All right, so here's my plan then. Thursday, we will talk about your last formative assessment answers. And I am also going to add a couple more story problems I will send out an email tomorrow as to what they are so that you can at least read over them and maybe get some ideas in your head, and we'll talk about those on Thursday. And that'll be it. Cool. Well, thanks for being here, folks. Let's see, today is Happy Garbage Day, which means I say, hope to see you on Thursday. Office hours are tomorrow if anybody wants to talk to me. Hang in there. See you next time. Thanks for being here, Zoomers, as well.